Welcome to my project called Explainable AI Models for Edge Case Object Identification in Autonomous Vehicles. In this project, I explored the AI model's performance in terms of predicted accuracy and explainability for object identification in challenging edge case scenarios within autonomous driving. Nowadays, AI has transformed autonomous driving, but real-world challenges like poor visibility, bad weather, and broken infrastructure can compromise performance and raise safety concerns. While accuracy in ideal conditions has been well studied, there's still much to learn about how models handle edge cases and how transparent their decisions are. That's where my research comes in. I evaluated two well-known pre-trained models, ResNet50 and VGG16, to see how they handle these edge case scenarios. Unlike traditional studies that focus on detecting individual objects, I look at how these models classify entire things, like a car in snow or a scooter in fog, representing the kinds of complex environments autonomous vehicles deal with. To test this, I collected a dataset of 8 edge case images, including night driving, rain, fog, and snow. But it's not just about whether the models get it right. I wanted to know why they make the decisions they do. To do that, I used 3 explainability methods: Lime, Grad-CAM, and Anchor's explanations. These techniques help us interpret the model's predictions by highlighting the features they focus on. This is critical because it's not enough for AI to be accurate. It also needs to be understandable and trustworthy, especially when it's being used in safety-critical areas like autonomous driving. I have detailed experiment analysis for each of the 8 images in this manuscript, and you are welcome to take a look at the experiment analysis further. Here, I want to highlight the key insights from this project results. In testing ResNet50 and VGG16, I found that both models perform well when objects retain their general shape and key features. For example, broken road signs, cars, and scooters in fog were accurately classified because the models relied on features like text or the overall shape. However, their performance dropped significantly in more challenging scenarios, like pedestrians in rain with umbrellas covering their heads or cars partially buried in snow. In these cases, the model struggled to interpret the visual context and frequently misclassified the scenes. Let's talk about the explainability methods. Lime provided localized visualizations, which were helpful in highlighting specific areas of the image. However, it often focused on irrelevant regions or gave inconsistent explanations, especially in cluttered scenes or low visibility conditions. Grad-CAM highlighted broad regions of the image, but it lacked clarity. For example, in foggy or dark scenarios, it focused on the car and its surroundings without differentiating which features contributed to specific predictions, making it less actionable. Anchors, on the other hand, provided the most precise and interpretable insights. It excelled in linking critical features, like the shape of a scooter or a text on a road sign, to the model's predictions. However, it had low coverage, meaning its explanations were highly instance-specific and didn't generalize well across similar cases. Here I have a key table summarizing the analysis conclusions for each individual experiment. As a final conclusion, ResNet50 and VGG16 performed similarly, showing strong classification in clear conditions, but struggling with occlusions, poor visibility, and overlapping objects. Among the explainability methods, Anchor stood out for precision, Lime was flexible but inconsistent, and Grad-CAM, while efficient, lacked differentiation. These findings highlight the need for future models and explainability methods to better integrate contextual reasoning and improve generalization for real-world conditions. This research contributes to understanding where AI succeeds and where it still has limitations, paving the way for safer and more interpretable systems in autonomous driving. I have included visualizations of each image's output using Lime, Grad-CAM, and Anchor's XAI methods for both ResNet50 and VGG16 in the appendix. These visualizations provide valuable insights into the strength and weakness of each XAI method across the models. I encourage you to review the full manuscript. Thank you very much for watching.